Welcome once again to the Transistor lecture series. Now in this lecture, we'll try to explore the common collector transistor configuration. So here you can see the circuit diagram for common collector configuration for NPN and PNP transistors. These are shown. So it is quite obvious that the collector part is common to both the input section as well as to the output section, and we can see the output we are taking between the terminal collector and emitter. So here we can observe a few things. This is the input section, and this is the output section. So naturally we can see the input current is IB. So just like C configuration, it is in CC also IB is the input current, but the output current here is now IE, and input voltage between the terminal base and collector. So input voltage is VC VBC. So VBC we have here, and the output voltage we have between these two terminals. So that is output voltage is VCE. So these are the input and output parameters. In addition to that, we have the input resistance Ri and output resistance R0. So these are the parameters associated with the common collector configuration, and our discussion will be based on these parameters. Now same thing will be valid for the PNP transistor as well. So here we have used NPN transistor, and here we have used PNP transistors. So now the current amplification factor, which is denoted as gamma for the common collector configuration, it is denoted as gamma. So how the current amplification factor is defined? It is the change in the output current with respect to the change in the input current, keeping the output voltage constant. So you can write that output current is IE. So change in IE to the input current IB with the output voltage constant. So VCE is the output voltage which is constant. So gamma is defined as this ratio. So that means it is quite natural that alpha, beta, gamma, they are related with each other. Now let us explore the relation among alpha, beta and gamma. So earlier we have seen that alpha is given as gamma is given as delta IE divided by delta IB. Then alpha is given as delta IC divided by delta IE, and beta is given as delta IC by delta IB. So these three relations we already have. Now let us consider IE, that is equal to IC plus IB, which is applicable for all kind of configuration. Hence the change in IE can be given as change in IC plus change in IB. So here we can write delta IB, that is equal to delta IE. Okay, so here you can write delta IE minus delta IC. Now if we substitute this delta IB in equation 1, so let us call it equation 4. So from here to in this equation, if we substitute the value of delta IB, then we can write gamma is equal to delta IE divided by delta IE minus delta IC. So if we take delta IE at the numerator, then we can write it like this: 1 minus delta IC divided by delta IE. Now what is this delta IC by delta IE? This is nothing but alpha. So we can further write gamma is equal to 1 by 1 minus alpha. So this is an important relation. So call it equation number 5. So gamma is equal to 1 by 1 minus alpha. And earlier we have proved that 1 by 1 minus alpha, that is equal to 1 plus beta. This one you can prove once again from this equation as well, but I am not showing it here because in our previous video we have already proved this relation. So we can say that gamma, that is equal to 1 plus beta, that is equal to 1 by 1 minus alpha. So this is the relation between alpha, beta and gamma. Okay, so next we'll try to find the expression for the output current. Now here our output current is IE. So we have to find the expression for IE. Okay, let us start with this popular relation. IC is equal to alpha IE plus ICBO. Okay, so and also we know that IE is equal to IC plus IB. So now if we substitute the value of IC from this equation to this equation, then we can write IE, that is equal to IB plus alpha IE plus ICBO. So from here we can write, if we take this thing in the left hand side, we can write 1 minus alpha into IE, that is equal to IB plus ICBO. So further we can write as IE is equal to 1 by 1 minus alpha into IB plus 1 by 1 minus alpha into ICBO. So this is one relation. We can note this in terms of alpha, IE in terms of alpha, and ICBO and IB. Now another relation we can have, we can replace this as gamma, because 1 by 1 minus alpha, that we have seen as gamma. So we can also write this is equal to gamma IB plus gamma ICBO. So this is another relation in terms of gamma. And also we have seen that gamma is equal to 1 plus beta. So we can also write IE equal to 1 plus beta IB. IB is our input current, right? So, and this is 1 plus beta ICBO. So this is another relation. So we can write the output current IE in terms of alpha, beta, gamma, all three. So these are the parameters associated with common collector mode. Now this common collector mode configuration, this is having interesting application, because this is the only configuration where we have the high input resistance. High input resistance. So that means Ri is high and very low output resistance. So that is R naught is low. In previous cases we have seen that low input resistance, high output resistance, but here we have it the other way. Now due to this reason, the voltage gain provided by this circuit is always less than unity. So here we are getting voltage gain less than unity, whereas current gain sufficient current gain we are getting, that we have seen from the gamma. Now therefore this circuit is hardly used for amplification, seldom used for amplification, but relatively high input resistance and low output resistance of this circuit. Now it is used for impedance matching. What is impedance matching? Suppose we have some device, say this is my device 1 and this is my device 2. Now this is having high output resistance, so R not high, R in low, so low input resistance, high output resistance. Now device 2 is also a similar device where you have the low input resistance and high output resistance. R naught is high. Now if I want to connect them back to back, then we'll be getting something called loading. Loading means two resistors. Suppose here if we have say 100 kilo ohm resistor and here we have 10 ohm resistor, if we connect them in parallel, then the equivalent resistance will be less than or equal to 10 ohms. So that means this high resistance will be loaded by this low resistance, and as a result of that there will be impedance mismatch. So here we use something called unity gain amplifier. That means it will do nothing. It will do nothing. So we call this device as buffer, which is having high input resistance. Here input resistance is high and output resistance is low. So as a result of that, here I am not getting any gain. It is just delivering what it is receiving. From this terminal to this terminal, it is delivering the same thing. So buffer is also known as unity gain amplifier, and this buffer purpose the common collector mode is used, and it is very often used as often called as emitter follower, and many a times it is used in a Darlington pair. I am not elaborating this term here, just uh, get accustomed with this term. Something is called Darlington pair. So common collector mode transistor, two transistors, they are used in a pair which is called Darlington pair, and this buffer is also popularly known as emitter follower. So these are the important terms associated with the common collector mode, and it is having a very important operation or application for impedance matching. So we end here our discussion on the common collector mode. Thank you.